So now we're going to take that one-dimensional motion from velocity to acceleration. So I've given you some math notes that really help, and now we're looking at velocity, and we want to make sure that we understand what our average velocity. It's a vector. It has direction and magnitude. Remember, speed is just a magnitude. And we've seen how this change in position and change in time relate to instantaneous velocity or average velocity. So our average velocity here has our change in displacement with respect to time. It's a vector. It has magnitude. Of course, we're in one dimension. So now we're going to talk about acceleration. And we actually mentioned this a little bit, that I could have a constant acceleration. And in Physics 1 here, we're going to utilize that special case of constant acceleration. Ultimately, when you get to dynamics or you get to more mechanics, you're going to be able to have that variable acceleration. And even in our CATS textbook, we're going to look at a couple of times where we're going to have not just a strict constant acceleration, but we'll be able to break it into parts with that constant acceleration. So acceleration in and of itself is defined as the rate of change of velocity. So we're going to look at that rate of change of velocity, okay? So we've already talked about how the velocity is a derivative of a function with respect to time. But acceleration will ultimately be a second derivative with respect to time. And I'll kind of link that back in here. But for right now, we're going to look at that average acceleration that we're talking about. And hopefully it's going to be a constant acceleration. And we're going to define that as a change in velocity. Again, velocity is going to be a state function here. We're going to look at our final velocity minus our initial velocity. And then we're going to look at time. Now I want to kind of focus on some units initially. So on the top up here, we've got units of meters per second, and on the bottom we have seconds, and we can treat those units mathematically. So we're going to end up in units of meters per second squared. Okay, seconds times seconds is seconds squared. So we're going to have those units, and we're going to have the same thing that we saw in our velocity, that there's an instantaneous value. And we can do the same thing here. We can take that limit of the velocity. As the velocity goes to 0, we can look at that tangent to the curve on a velocity versus time graph, and we can get that instantaneous. So let's kind of look at what we have. So we could have motion where we have a uniform velocity where the arrows are going to represent the magnitude. The longer the arrow, the bigger the velocity, okay? And in this case, we've got the car traveling down the road. It's probably on cruise control, and our velocity arrows are all the same. They're all the same, so we're traveling at a constant velocity. If I have no change in velocity, now remember, this is direction and its order of magnitude. I have direction and magnitude. Because when we start dealing with circular motion, I could be traveling at the exact same speed, but because I'm constantly changing direction, I also have the potential for an acceleration. But in one-dimensional motion, we're just going to be dealing with the fact that my velocity is going in there. So my acceleration is going to be 0. My final velocity is equal to my initial velocity. My final velocity minus my initial velocity is now 0. I have no acceleration. But now let's look at that case where we're at the stop sign and we're trying to get to speed, or we're coming in on the on-ramp onto the interstate, and I'm going to look at it from there. So in this case, you can look at my velocity arrows. They're changing their size, right? They're getting longer. My acceleration arrow, though, because acceleration is also a vector quantity, it's going to also have that vector quantity. The acceleration is uniform, they have the same length, and my velocity is increasing. So in this case, I have a positive velocity and a positive acceleration as well. Acceleration can be negative. And when we have a negative acceleration, it's called a deceleration. Okay? When we have a negative acceleration, it's called a deceleration. Or we can have the negative show us our direction. For example, we will use gravity because gravity is a constant acceleration. We're going to use the value of 9.8 for that constant acceleration. So if I have a ball that I'm dropping, it's going to experience a constant acceleration. and we're going to use that negative to give us direction. But if I'm dealing with a car going from 50 miles an hour to 20 miles an hour and I've hit the brakes, that's going to have a negative because it's a deceleration. Okay, so we're going to have that particular aspect that we're going to have to look at. So we're going to keep that in mind. Now, I want to refer you to section 2.9 in your book. Okay, you want to go to 2.9 in your book, and this is our special case for constant acceleration. I want you to refer to table 2.4 in CATS because that's going to be your kinematics toolkit. You're going to use that kinematics toolkit. That section 2.9 will give you the references of how all of these equations came about. And that's one of the things I want you to kind of think about, and I want you to kind of do a reflection on how do we get those equations. So when we come back, we'll talk about that, and we'll have a great day.